think it's difficult because this kind of limitation, it did happen very, very early when the method was derived. And then at some very late time, you try to do something to overcome this limitation that was introduced very, very early. So sounds very challenging for me.
Welcome to episode 73 of the Engineer Mind podcast. I'm your host Yusuf, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. In this podcast, Eugen and I talked about the Lattice Boltzmann method and its applications, why GPUs are working so well with this method. We tackle the question on the weak compressibility of LBM and how the Mach number defines it. We talk about numerous advantages of the method, its inherent simplicity, parallelization aspects, and boundary condition treatment, and we will also cover the aspect of turbulence models, blending functions, problems and solutions. We also cover the future of the Lattice Boltzmann method and so much more. And now, ladies and gentlemen, here's my podcast with Eugen Riegel. Hey Eugen, thanks for being on my show today.
Thank you for having me.
Very interesting. So this will be the first podcast on the Lattice Boltzmann method, short LBM. But before we jump into the nitty-gritty of the LBM and what that actually means in terms of simulating fluid flows, for example, can you give us like a 1, maybe 2-minute bio? Who is Eugen and what are you actually doing?
Yes, sure. So I'm Eugen. I am the CEO of the company Numeric Systems. I founded in 2016 after investigating long time on LBM research and development of a software which is GPU accelerated and should employ GPUs for very, very fast simulation of fluids using the LBM simulation technique. And I've started all of this during my studies. Basically 2007 was the ignition. And this was my second study of aeronautics at this time. And my first study I studied before, it was information science. And this work gives me the ability to bring both my interests together.
Very interesting. You talked about the Lattice Boltzmann method, and as I already mentioned previously, this is the first time we have someone as a guest talking about LBM. Maybe give the audience kind of an overview. Why is LBM method so intriguing? Why would we use it in the first place?
So LBM is another approach to explaining fluid behavior on a continuum basis. In relation to the Navier-Stokes. So Navier-Stokes is the older approach, which was researched already for a very, very long time. The Navier-Stokes method is based on our impression of how fluid behaves. So scientists went there and investigated how does fluid behave if you this and that to the fluid. So what could be the fundamental things that are governing this fluid flow. And LBM, it comes from the other side. It comes from the molecular perspective. So it does more count on a statistical interpretation of how particles move or how atoms move. And this is a completely different approach to Navier-Stokes, and it ends up also in a very different mathematical description of the equations. And these equations, they are very, very simple. So they come down to use only simple arithmetics like addition and multiplication operands, and that's all you need to get to a fluid prediction. And this makes the method very, very cheap in computation, easy to implement because you don't have to deal a lot with specific schemes of discretization. How we usually do if you do Navier-Stokes implementation, it comes at a very, very cheap start. And what is also very interesting about this method that it is inherently transient. So you have a formulation which also models the time. So all the 4 relevant dimensions are captured by these very simple equations, which are the 3 spatial dimensions and one time dimension. And this is what makes it very, very attractive. So it's simplicity, but complex things comes at the second place with this method. There are many about them, but this is what is very, very exciting. It's very, very simple. It's very easy to start. And the other thing which is interesting for what we do here is that it's very easy to get parallelized on a highly parallel processor like the GPU. So from the theory, you can compute each cell. You can update each cell in your simulation domain independently from all the other cells. And this makes it very, very easy to parallelize. Yeah, of course, the beginning is again very, very easy. The difficulties come later, but this is what makes this method very nicely suited for highly parallel simulation with GPUs.
Super interesting. Thanks for explaining this, Eugen. And when we talk about speed, obviously we come to the differentiation between GPUs versus CPUs. So obviously, Pacefish uses GPUs, which achieves much higher performance compared to the classical CPU approach. Can you give us like your own explanation of why GPUs perform better in this case using the LBM method than the classical CPU approach?
Yes. The simplest explanation is that the bandwidth of the memory on the GPUs is far higher than if you look on CPU systems, CPU-based systems. So normally, a lot of LBM implementations, they are not limited by the number of computations per second which a computing device can do. For example, a CPU can do that much, a GPU can do a lot more. But in the end, it's an algorithm which is bounded by the memory bandwidth, and this is 20, 30 times higher on a GPU than it is on a CPU. So it's, for example, even our implementation, which is not that slow on GPUs, it could run even faster on GPUs if the memory bandwidth would be faster, because the GPU can deliver much more computations per second that we are able to get out in our algorithm. So this is why it's faster from the architectural point of view of the hardware.
Super interesting. And obviously, when we talk about simulation, like discretizing a domain into smaller elements, then we talk about obviously the mesh size or the grid refinement. How does the LBM approach this grid or mesh refinement, especially in the near world regions? How does that work?
Yeah, so basically, the fundamentals of LBM, they don't cover grid refinement. So grid refinement is something that is not like coming out of the formulations by itself. It's a little bit artificial to the method, because the method itself, how it's formulated, is it assumes that you have uniform grid refinement everywhere. So you have a Cartesian grid, which is always having the same size, and the particles are then assigned to specific locations which are regularly placed, and this particle, they contain a state. And if you introduce local grid refinement, which basic idea is like you have a large cell and then you cut it into smaller cells. Typically, Oct3 approaches are used for 3 dimensions. So you have one large cell which comes down to 8 cells in 3 dimensions, and so this is something you can do by having according to limitation of software, but the method itself, it does not like it. So it changes if you the size of the cell have some implicit effects on the state of the cell. If you, for example, change the size of the cell, you also change the time step. Yeah, because for example, for something to travel to travel a smaller cell size, it needs also maybe half of the time it will require on the larger cells. And by this, it changes a little bit the background of the formulation of the LBM state. And because of this, it's not that ideal to use local grid refinement, but in the end, you have to use it for industrial applications, because if you refine everything with a high resolution, you will end up in super large simulation domains, which will not be able to fit anywhere. So you have to use it. And so there are a couple of approaches which glue together the zones of higher refinement and lower refinement to make sure that some things stay consistent. And in the end, the difficult things, they do not happen at the wall. If you do the refinement, the difficult things in that context, they happen between a higher refined and lower refined region in the far field. And you have to pick basically in the end if you want to have a consistency in the mass, or if you want to have the consistency in the shear. You cannot have both of them. So this makes it a little bit difficult. There are other methods which try to interpolate differently and to bring more consistencies together, but in the end there's always kind of suffering. So there's no free lunch here. But this is the basic idea. You use octrees, you refine a large cells to smaller cells, and do it by a factor of 2 usually. because this is the most effective approach right now. You can also do it in a refinement by factor of 3 on some integer value. You cannot like lose some value which is not which is a fractional value. So this is what is here very relevant. And I'm not sure if I answered this question here.
Definitely, Eugen. Now, you mentioned this information transport aspect, which is usually known, let's say if you study basic computational fluid dynamics, it's known as the Courant number. Usually this is how you learn it. Is there like an equivalent counterpart in LBM called the Courant number, or how is that taken into account, the information transport?
So if you run an LBM simulation, you basically deal with LBM specific units. So for example, the velocity, if you model it inside the simulation, you basically model is not like a velocity in some unit space like ours, like the metric unit space, meters per second, something like this. It is converted by modeling as a Mach number. So all your velocities you have in your simulations are Mach number velocities. And in the end, you are limited in the value which you should not exceed during a simulation runs as a local velocity. So for example, for us, a limit is around 0.3 Mach number. If you go beyond this in some cells in a simulation, you basically can end up with an unstable simulation, so the simulation can crash. So then you have like NRN results everywhere, or you just will have some impact on your results in your velocity field. And the background of this is that that when the LBM equations are derived, Maxwell equation was linearized around a Mach number of 0.0. So at rest. At this like state, the statistical velocities of the particles or atoms were like derived, and this was then integrated into the simple LBM equations, and this results in the case that if you like deviate from a Mach number of 0.0 in your like local state, you basically deviate from this linearization point that you have applied when you have derived the method. And this is why also like inaccuracies become larger and larger when you get more away out, when you get more distant away from it. And this is why this is the kind of a limitation that we usually see. So 0.3 is our limit, or we suggest if our customers use our program that they not exceed its number, and then they are on the safe side. So this is basically the pendant of the CFL number from the United States, for example.
Got it. When we talk about compressibility, also you said the limit was 0.3 Mach as a Mach number. Let's say someone wants to use the LBM method for compressible flows. Would it still work? Are there other methods? Like I've heard something about in the past, entropic LBM. Is it still something that's used today, or are there new methods coming up for compressibility?
From my perspective, it's still under research. So there's nothing like really working there, which allows LBM to be used like in the supersonic regime. Like if you have a velocity of a Mach number above 1, or if you have like a Mach number which is 0.7 or something in that range. There's some research work ongoing. To be honest, I'm not that strong in that, so I don't read this because it's out of our scope here at Numeric Systems. But I've seen that some people try to work around this kind of limitations and get away with it, to get maybe the application field wider, like to use it for some aeronautical applications with some airplane simulations, stuff like that. But basically, I think it's difficult because this kind of limitation, it did happen very, very early when the method was derived. And then at some very late time, you try to do something to overcome this limitation that was introduced very, very early. So sounds very challenging for me, but of course nothing is important. It's interesting to see that, but as I explained, it's not in our focus right now, because here at Numeric Systems, we with our development of our software, Pacefish, we focus on automotive applications or applications in the AC field, like simulation of wind load on buildings or bicycles or things like that. Yeah.
Got it. Maybe to talk one more time about maybe going one step back to the mesh. Can you explain if there's something, and I know this question will come up a lot, in the LBM method, is there like an equivalent of the Y plus value? Is that even used? Because from my perspective, or what I know, it's not used like explicitly, this Y plus value. Or is it still used, or can it be used?
Yeah, well, we have it in our implementation in Pacefish. We deal with the Y plus number, but it is something that is related, not necessarily with the LBM or the Navier-Stokes world. It's related with the way how you model the turbulence. And the Y plus number is something very important if you like use specific wall models or turbulence models, which employ a wall model, so that you have like to model the wall resolution in a way that you don't go like too fine in the wall region, not to get into the viscous layer or the buffer layer of a turbulent boundary layer, for example, because then the wall model implementation, which is used at that position, is not able to account for this, because then it will leave it like it's usability window. For example, as I remember from, for example, OpenFOAM, you should, if you use a K omega SST based turbulence model, you should derive a mesh for a simulation, unstructured grid mesh, which is staying with your local Y plus resolution above 30, for example, or 40. It shouldn't get closer to it. This is something that we have learned very, very early. So this kind of approach is not feasible with LBM, because in LBM, if you deal with LBM, you are basically jailed to this structured grid. So you have to stay in your Cartesian grid world, where you can like refine if you want, like to get finer at the wall to account for shear gradients and stuff like that. But you cannot provide a geometry adapted mesh here without like using a different method, like another Stokes method, just for a thin modeling of the boundary region and then like blending to some LBM based simulation outside. This would be like, it's also possible technically, of course, but yeah, the efforts are high and then the benefits are questionable, at least. What will put to bring this to you? You have issues for both sides then in the end. Yeah, and so you are jailed, as I explained, in this world where the geometry dictates you the intersection of how a cell is cutting your geometry. So you have all the complexity is then at the wall in this moment. So you can have any like arbitrary cut schemes if you have a Cartesian grid cell, a voxel, we basically say, and you cut it with some arbitrary part of a geometry. And in other places, for example, you can approach this by an immersed boundary approach, for example, that you like estimate the forces that will act between the geometry and the cell, and then you like employ only the forces. We use a different method. We don't use immersed boundary here, but what we have done in Pacefish is we have achieved an integration of the K omega SST, of the classical omega SST based turbulence modeling, like you know it, for example, from steady state run simulations, but also we have some variants which use LES in the far field. So, for example, the delayed attached eddy simulation approach, DDES, or improved delayed attached eddy simulation, IDDS. And this has become possible because we have overcome this problem that appeared there because of the Cartesian grid limitations at the wall by some specific numerical discretization that is like unique. It's a part of our secret sauce here, which has allowed us to implement the K omega SST based turbulence modeling, also in this classical world, like which like deals with Y plus numbers. Yeah, it's important there which Y plus resolution do you have locally, but our like implementation allows us to overcome these limitations in terms like we can allow our customers to provide a mesh which is going also very, very low in Y plus number. So for example, if you have you have a bluff body and you have some place where the flow is detached, then in the recirculation wake, typically the fluid velocities are much slower, and because of this, also the Y plus the Y plus numbers are very low. And normally, with the classical turbulence modeling implementation approach, you will require there a more costly solution. With our approach, you don't require this. You can just provide this to our implementation of the model, and it automatically compensates the situation that you have a locally lower Y plus number at the wake, as you, for example, have at the front part of the geometry, where you have, for example, I don't know, Y plus number of 50 or 100 or 200 or even 2000, and in the wake region you have maybe only 1 or 2 or 10 or 20, and this is something that it was very difficult with the LBM because of the limitation to the Cartesian grid discretization mesh. We have found a way to work around.
Mm-hmm. Back in my time when I was at SimScale, I know that your solution is very fast. When it comes to multi-GPU acceleration, like how many GPUs can someone use at one time, and how many cells can you, for example, simulate?
Mm-hmm. Yeah, so the largest systems that one can use with our software is consisting of 16 GPUs. The limitation that we have right now is that they have to be organized in one single node. Like, we do not offer a polarization over several nodes, but this is normally also not required, maybe for some academical cases, but for industrial cases, you don't need it, because if you count it in one single GPU, if you count it as 64 gigabytes, you can fit in there already 200 million cells in just one GPU. And if you say you have 16 of them, then you can have a 3 trillion cell simulation in one GPU system, which is more than enough for for many applications that we do. And so this is like the high limit. Production cases that we typically do, it depends a little bit on the application field. So, for example, one of our customers who use our software for truck simulation, truck aerodynamics, they have a simulation which has a size of 300 million cells, and we run typically this setup on a 4 GPU machine. So we don't even use 16 GPUs. We have 2 machines on our side, 2 with each 4 GPUs. And this allows us to run such large simulation cases. And this runs, they usually take maybe, well, this is already a large simulation. It takes 20 hours or something to finish. But yeah, for example, if you talk about SimScale is running many simulations from the construction people, like architects and construction engineers. And they have even smaller simulations. So they have maybe simulation of only 40 million cells, and they finish within maybe only 1 hour on a 2 GPU machine. So this is very fast. So people are often surprised by how fast they get the results.
Yeah, it's really crazy to think about that. We now covered a bit of the processing part, like when we talk about GPUs. When we talk about pre-processing and post-processing, what sets your solution apart from other solutions in the LBM space, or even solutions such as OpenFOAM? When we talk about, let's maybe start with pre-processing. What CAD formats are you working with? How do you maybe clean the geometry? Is it done on the fly while someone imports the geometry? How does this work in particular?
So one of the benefits of our implementation is that we have very low requirements on what is provided to the software as a geometry. So the idea is to eat everything the customer gives. So not to crash and not to deliver stupid results. And our role model implementation is very robust. So basically, you can provide us anything which is displayable as a triangular shell. So basically, we use STL input file format. So if there's something you can output as an STL file, you can put it into Pacefish, and it will be able to run a simulation on it. And for example, the typical issues that we don't have is that, for example, that our preprocessing is stable to, for example, some sharp contours of the input mesh, or some very complex shape edges or whatever, where you, for example, if you have a mesh generation, for example, from OpenFOAM, maybe Hex Mesh or any other tool, like which has the role to generate something which extrudes your input mesh in a smooth way. There are many challenges at nicks and at corners and so on. So this is something where our role model is completely immune against. Another like typical challenge is that often geometries are not watertight. So with other solvers, you would not be able to run the simulation mostly. In our case, well, if you really want to give it into the simulation, you can do it. The bad thing that you can, or the worst thing that you can like see is that you will have a lot of internal flow inside the simulation, like because of some hole. There was an opening in the geometry shell. There was like an opening which connects the internal and the external volumes, and through this like hole, fluid can pass. And because of this, the simulation decides to put like inside this also fluid cells. It comes at an expense, so you have to spend computational cells on this region. But you can also use some tweaking parameters in our setup, which, for example, allows you to define a threshold size of a gap. And if there's a hole in your geometry definition, which is like smaller than this threshold, then this gap will be ignored. And then you can also run a simulation, for example, of a car pre-study, which is very coarse, for example, with very low effort on cleaning up, or almost no efforts on cleaning up the geometry, just loading inside Pacefish, maybe iterating a couple of times the preview of the mesh generation and see, okay, do I have some internal flows where I don't want to have some, and then tweaking this parameter, and maybe also some other tools that allows you to improve this, and then just finish up the pre-processing and go on with the simulation run.
This is so interesting. Yeah, it gives me brings back memories when I used OpenFOAM, for example. You have like a broken geometry and you try to run a simulation on that. And as you said, the water tightness, it's such a pain in the ass. But yeah, very exciting that Pacefish, your solution, tackles this very elegantly. When we talk about post-processing now, which is the last step, how does that work actually? Like how can users export results?
So we try to open up a large space for the user to use different tools for post-processing. There is some kind of post-processing that is done inside Pacefish. So this covers, for example, the averaging, because as I explained in the beginning, LBM is an inherent transient method. So you get simulation with time. It's not the same like if you have a steady state discretization method from Navier-Stokes. So it's just the steady state method enforces like the time to get away from the equations. In our case, we run the simulations time step by time step, and we do like true averaging during the simulation runs. And this works by a process which is like after the simulation was running for a while and is already settled. So our simulation, and this is almost it is true for all LBM simulations. So it needs at the beginning some time like to converge. Yeah, it doesn't converge in a strong sense, but the state of the fluid is then ends up with a repetitive topology. Yeah, so it runs, it goes with time, but you see the same structures to appear again, and then you see, okay, now the simulation did converge. And then you start the averaging, and the averaging is interrupting the simulations after each couple of time steps. You can define this in our setup, how frequently this to happen. And then the current snapshot data set is committed to the running average. And then in the end, you can have access when the simulation ends, to this average solution, which was accumulated over a given amount of simulation time. This is something that is done already in Pacefish. Then we export the data in formats which allows you. Well, we use the NZ Gold format for the three-dimensional data export. You can use also CSV file exports. So if you want to have the data in a tabular way, for example, you want to post-process some pressure probes or whatever, depends what you want to do. Of course, if you have a lot of data you want to export, you should put it to a CSV file because it then explodes. We have invested some time to allow, for example, the transient data set is exported by Pacefish to get imported into OpenFOAM in a subsequent, for example, spectral analysis. So you can use our transient export of some, for example, pressure distribution on some surface, and connect it with some spectral processing with OpenFOAM, and then connect it to different tools in the post-processing field. So this is how we usually work. So our post-processing world is like ParaView for the most stuff, Excel, and OpenFOAM noise tool. It's a tool which is noise for the spectral analysis. And so this is like where we like officially end up. So right now we also don't want to cover specific post-processing tools or develop our own, because we think that, especially with ParaView being there, there's a very, very powerful tool available. So the demand is like not that strong to provide something specific from our side.
Definitely. You talked about the running averaging, basically the statistical operations that happen while post-processing the results. Is that something that's really beneficial for the user in the sense of that don't have to do the statistical analysis once they've got the results? So that's already done inside of Pacefish, if that's correct.
Mm-hmm. Yeah, so the great benefit here is that you don't have to handle that big amount of information, because if you think about, okay, a simulation is having 300 million cells, and you want to run a statistically average solution, or you want to have a statistically average solution in the end, and you will write out all this information to perform the averaging later, you will be required maybe 1,000 snapshots to add up with some numbers that you can trust, like a good variance and a good average. And so you have 300 million cells, you have to multiply it with 1,000, so you have 300 billions, and you have to write all this data to disk. So there's a lot of lack of information which is not written to the disk. It's not like going into any I/O pipeline, which is just like crunched by the GPUs and by the CPU, and in the end, like delivers you just the result you want. So this is something that will be very, very costly by the customer to be replicated, and this is the great benefit, and this is also why we have integrated it inside Pacefish.
Got it. One last question, maybe before we jump into the application space, like where your solution can be used for, or what your solution can be used for. You talked about different turbulence modeling, which is, if I'm not mistaken, DDES, you said, IDDES, as well as URANS, which uses the Omega SST model. Yeah. Why those? And is there a need for another turbulence model? And if yes, why? And if not, why not?
Mm-hmm. Yeah, so why we have used this? So this is a bit... well, there was a historical development in this sense. So when I was still studying and I was writing on my thesis, the idea was to look out for something that works in the targeted application field. And the target application field this time was automotive industry. And this industry, they typically, like the production simulations, they use K-epsilon simulations or K-epsilon based turbulence modeling, for example, with extra power flow at this time. And also, if you have looked on applications, the automotive field with star CCM or ANSYS, they use K-omega SST. And this was some model which is the people already trust on the customer side. So you do not have, if you come out with too many new things, what is then happening is that nobody is believing to you, because they don't see any they don't see some things that they already can trust to, and so you have a big question behind your offer, and this is very, very critical if you sell a CFD solution, because having the customer's trust in your result is very, very important, and this is why we have decided to try to implement something which is already existing there, and this is why we try to do K-epsilon. But with K-epsilon, I made the experience that it is it is not fully integratable to the wall. So at the wall, you have to use some wall functions and things that make it very, very difficult to incorporate it with our solution. On the one side, and the other side, also the results which K-epsilon delivers usually they are not easier. So K-omega SST delivers better results than K-epsilon, and it's also integratable to the wall. So you have the K equation, you have the omega equation, and you can explain for both of these equations how is the individual K or omega number developing until it touches the wall. And this is very important in our implementation approach. This is why we use K omega SST then. Well, it took us a lot of efforts to get there, but this is why we wanted there. On the other side, the idea was like to use something just LES based, like for example, the Smagorinsky turbulence model, which is employed by many other like LBM developers or universities or other companies which try to run LBM on all those GPUs. But the problem with Smagorinsky is that you have well, in the far field it works very good. Yeah, so if you are away from your geometry, you have only the weight which you have to simulate. It works very good. But if you want like to simulate the situations at the vicinity of the wall, like the boundary layers, it gets very difficult because your turbulent length scales are becoming smaller and smaller the closer you come to the wall, and because of this, you will require an infinitely high resolution, just to say it very clearly, close to the wall, which is extremely expensive in LBM. So as I explained in the beginning, when you like refine a cell, we have one cell in the beginning. You refine it just by a factor of 2, you end up with 8 additional cells. Yeah, and then you can think about, okay, how much you have to adapt this refinement by a factor of 2 to get up to the to the resolution of the Kolmogorov length scales, and this will explode your simulation a lot. And the reason why this happens is that if you refine in Lattice Boltzmann, you refine all 3 directions at the same time, while in, for example, an unstructured grid solver, you can just refine in the 8th dimension, and the other dimensions you can keep. And this allows you like to go for this approach and use this kind of modeling in unstructured grid solver. But for LBM, in my opinion, it doesn't work. You have always to trick around at the wall with some other stuff, like you have to use specific approximation for the shear, or how you compensate this effect that you cannot resolve all of the turbulences that you would require to get to a good solution at the wall. And so this is why we don't approach this way, the dot strength sense. We do offer Smagorinsky in our implementation as well, but 99% of our rounds, they don't use it. So they use this K-omega SST based turbulence modeling because, especially with this DDS variant, you have like three regions in your turbulence modeling. You have very close to the wall. You have the K omega model, turbulence model, which is very strong in predicting the shear forces at the wall and how it interoperates with the turbulence generation and so. And then if you go to the logarithmic layer, it blends out to the K epsilon turbulence model, which has its strengths there. So this is basically the concept of the standard K omega SST turbulence model. And then with the DDS extension, in the far field, when you get out of the logarithmic boundary layer, it blends out to an LES model like Smagorinsky. And there you can like resolve the wakes and the vortices and everything in a very high-grained way, depending, of course, on your local resolution, but it works very robustly. And for now, this covers very good our requirements or requirements of our customers. But of course, there are some like shortcomings of the model, and this is the known like shortcomings of the K omega SST turbulence modeling is the, for example, inability to reproduce secondary flows in some specific geometrical setups. So, for example, you have the main flow direction in some device, and then, for example, if you have something that is rounded, and then it comes out to get a cornered exit, and in between you have like a transitional period, and there is a primary velocity direction which goes downstream, but there's also some like rotating velocities, some rotating regions in the corners, which also do exist. And for example, K-omega SST turbulence we cannot replicate them very good. We need other models to get there. But yeah. So it would be, for example, very nice for us if we would have the opportunity to implement the Gecko model, for example, from ANSYS. Maybe they will publish it soon. So let's see. So if that will happen, it will allow us also to get there. And it's known that these models are better they are better in terms of these limitations. And yeah, so for now, we are fine, but we are looking out for other more powerful turbulence models to get published in a way that we can implement them on our side.
Mm-hmm. But obviously, this wouldn't probably be straightforward. Like if someone publishes a turbulence model, this is probably a ton of work for you to implement, I guess.
Well, I'm very optimistic on this sense because that stuff that we have done to the K-omega 60 turbulence model, it's something that you can straightforward apply to any different approaches. So this is some mathematical numerical tuning, and it can be done with any like anything that you get in a equation based form, you can input it on. And this is why I'm optimistic. But of course, the idea is the one thing, yeah. Then you start, and then you realize on the way, okay, there's no free lunch.
Yeah, I get it. Yeah, very interesting. Eugen, you mentioned the automotive aerodynamics application area where Pacefish is active. We have pedestrian wind comfort that you mentioned at SimScale. Any other applications, such as maybe wind loading? Anything else that we should mention here?
Yeah, wind loading is something that we are working on. Especially for what is important for wind loading is to have transient inlets, so that you can have or what you say that the inlet velocity that is approaching your simulation is also transient, not like a steady state profile, but something that is also already containing the inherent. This is very relevant if it comes to predicting proper wind loading forces on some facade of a building.
Very interesting, Eugen. Thank you so much for explaining this. There are different usage options also when we talk about Pacefish. Obviously, we talked about one, which is using Pacefish as a web-based and cloud-based solution using SimScale. Any other usage-based models that you are offering?
Yes, so we are offering our tool also for on-premise usage, like the classical way. People have done CFD before, so for this you have your own hardware on site. So some desktop computer with some GPUs inside. One is already enough. So if you have one GPU, which is, for example, offering you 64 gigabytes, as I mentioned already, you can do 200 million cells into it, which is a lot. So, and then you can use our software like in a rich client platform sense on it. So we have a front end, which is a graphical application. You can click in this application. You can load your geometry there. You can place your geometry. You can define specific things like rotation of it, some surface properties like the roughness, or if there's something having like a porous region. So, for example, we have the Darcy-Forchheimer porosity model implemented, and all of this is provided via our graphical user interface. And yeah, so then you use our software as you have done it with the different tool like ANSYS, CFX, or Fluent, or whatever. And the big thing is that if you use it on site under your desk, you have basically a supercomputer placed. So this computer can outperform some very large system consisting of CPUs by running the simulations using Pacefish.
Really interesting. And obviously we talked a little bit about the future, Eugen, and maybe to wrap this podcast up, this very interesting session, by the way. So thank you so much for being on the show and explaining this in very much detail. When we talk about LBM evolving in the future, do you have any thoughts on how it might evolve in the future? Any new models that might come up? Any new collision operator?
So I think the method is still under strong research. I think it's also a little bit like hype, or it is seeing a stronger interest than it was before. So when I started working with it in 2007, I wasn't seeing that much of activity on universities, for example, here in Germany. Meanwhile, there are a couple of universities which have own research groups doing LBM, and in my opinion, there's a lot of open work in LBM area, and the main fields are row modeling and turbulence modeling, in my opinion. So this is where I see the strongest gaps to have methods which can solve industrial scale problems on for example, where we are on a high Reynolds number scale. So not low Reynolds number. I think for that level of application, there's already a lot of stuff available. But for high Reynolds numbers with strong turbulence, a lot of work still has to be done. And this is where I think the development goes into.
Interesting. One question that would 100% come up is, Eugen, what books do you recommend or what resources do you recommend to jump into LBM? What would you say?
Yeah, so I will recommend a few papers, which if anybody is interested in them, I can provide something from that short list that I have. Myself, I have learned it more or less by being throwing into it. So the idea when I started my work is to port some existing LBM code. And then I realized, okay, it's not that simple. And then I dig deeper into it, and I end up with reading papers. But I think it's a difficult approach for the beginner. So there are a couple of nice like summaries, some books from Let and Chen, but there are many Chens, and so it's difficult to say specific paper. But anybody can ask me if he's interested in a short list, and I can share a list of these articles, which are, in my opinion, a good start. Well, but in the end, you have to make your hands dirty in a way to understand details or to see what is like the beautiness of this method, but also what is like very, very difficult here, and where it may be better suited for which kinds of applications. And one thing, for example, what is very great about LBM is that it is having a very, very low numerical diffusion. So normally the numerical diffusion is something that you always have. It depends on your numerical discretization scheme. In other Stokes solvers you have it, and in finite element solvers you also have it. And the great thing about LBM is that for the advection step, like that kind that accounts for something is traveling through your simulation domain. This kind of process is modeled in the LBM by just a particle shift. So you have one particle that is at one cell, and for the next time that it travels to the adjacent cell. And this particle travels to 100%. All of it is traveling. And by this, the advection is perfect. So there is no numerical diffusion. And because of this, for example, you have many, many benefits in the granularity of your results. So you have a better quality of results if your mesh is even not that high resolved as if you compare it to some, for example, unstructured grid mesh. And yeah, so this is one of the things that you can learn if you study these articles. But as I said, many things you are only able to learn, or it gets visible to you when you start to implement something by yourself.
Good tip, Eugen. Thank you so much. Where can people reach out to you? Obviously, via your website, numeric.systems, they can reach out to you. Any other place they can reach out to you?
Yes, of course. I'm on LinkedIn. The people can contact me as well. And I'm Munich-based, so our company is Munich-based. So if people are in Munich, they can also reach out to me, and maybe we have a discussion in person. Yeah, this is during this Corona times. It was difficult to meet people, but I hope that this time will be soon over and we can also talk more in person.
No, fingers crossed. Any closing remarks from your side, Eugen? Anything that we might have missed on Pacefish or LBM in general? The last words go to you. Yeah,
there are many things we can talk about. I think this will end up with maybe 10 hours podcast. I'm very happy to have the opportunity to develop this method and also to offer something to our customers, a tool which is, in my opinion, having very, very nice, unique capabilities. We try to, in the moment we are in an application field which is a kind of a specific one. So we have, for example, we don't cover a thermal modeling, for example, and so we want to improve here as well and attach methods. But we are trying to make this together with our customers. And so if there's anybody outside which is interested in testing our method, testing our software, seeing if it's suiting his needs, and even if not, at the first step, we are always like interested in gaining feedback, what we could add, in which sense, to make sure that we do not implement something into our software which nobody requires. And this is something that I can offer to anybody who is interested in Pacefish or CFD, quick CFD application. Perfect, Eugen. With that being said, thank you so much for the very interesting session. Obviously, I will put links down to everything that you mentioned down in the description.
and also links to your social profile, your website, and so on and so forth. With that being said, I wish you a great rest of the day, and maybe we'll see each other in the second part. Who knows?
Thank you very much, Yusuf, for having me, and all the best for you.
Thanks.